Hello, welcome to this video. Today, we're going to look at the proof of induction. So, in the past, we looked at proving with induction. Statements that would be a bit very difficult to just start with the givens and end with what you want, and instead just prove one simple case and then show that for any case the next one is also true. So I gave some examples. I also gave some examples for induction that's a bit more generalized, but I never actually formally proved it. I did give a formal an intuitive explanation, which is pretty simple, which says that because the first one is true, and if something is true, then the next one is true. Then if one is true, then two is true. If two is true, then three is true. And if three is true, then four is true, and so on. So now I want to actually formally look at what we have in the givens, and then prove that we can say that it always works. So here's what we're going to do. So the givens are like this. We have two givens. First of all, if we have a statement P, then P of 1 is true. And the second statement is for all natural numbers n, we have that P of n means that from P of n we can conclude that P of n plus 1. And again, it's very simple intuitively. It's analogous to looking at domino bricks, and then the first one falls over, and if any one falls over, the next one falls over, so obviously all of them fall over. But to use induction, we do need, sadly, to prove it formally. So let's begin. So what we're gonna do is incorrectly assume that there exists a certain n that's a natural number such that P of n is false. And then we're gonna build a chain of statements that will eventually lead us to a contradiction, which will tell us that this statement is false, which will tell us for all n natural numbers, we will be able to conclude that P of n is true. Okay, so let's begin. First of all, what can we do from this statement? Well, let's maybe look at the set of all natural numbers, such that for them, P of n is false, because we're assuming that there's at least one that exists. Maybe there are more, so we're just going to look at the set of all of them. So it's defined. Now let's let S equal the set of n of all natural numbers such that P of n is false. And we are going to go from here. So this is obviously a set that just contains natural numbers. And there's a principle that's called the well-ordering principle that tells us that for really any set that's bounded from below, or specifically the set of natural numbers that's bounded from below by 0, no matter if the set is finite or infinite, as long as it's not empty, we can say that there is a minimal number there. Now I might do a formal proof of this in the future, but for now we can just use this as also another given, as another theorem. And it's also very intuitive. And because of this statement, we can say that this set cannot equal the empty set. Meaning that now we can use the well-ordering principle to say now that we will let k equal the smallest number in the set. So it's the minimal n such that n is in S. So now, let's see. By the definition of k, that it's the minimal one in the set, we can break it down into two cases. Well, first, either k is 1 or k is not 1. Very simple. Okay, so now let's break down into cases. So let's look at case 1. K is equal to 1. Well, in this case, we get a contradiction. Why? Well, because it's a given to us that P of 1 is true. And so we can say that in this case, because K is in the set S, we know that P of K must be false. So P of 1 here is false by this, but it's given to us that P of 1 is true. Nothing can be true and false at the same time, so so this is a contradiction. This is a symbol of contradiction here. Okay, so this is case 1, very simple. Now let's look at case number 2. So in case number 2, if case number 1 is k is equal to 1, what will be the second case? K is not 1. But more specifically, because k is a natural number, I will write k is bigger than 1. Well, if k is bigger than 1, then I can safely say that k minus 1 is a natural number. So if k is 2, 3, 4, and onwards, k minus 1 will obviously be a natural number. And that means, because of the definition of k, so let's write, by the definition of k, we can see that k is the smallest one, for which P of k is false, meaning that any natural number smaller than k, P of it will be true. So we can say P of k minus 1 is true, but by rule number 2, given number 2, we can say that this implies that we just need to add 1 to k minus 1 to get that the next number is also true. So from here we get that P of k is true. But that's another contradiction, because we assumed in this case that P of k is false, which just because by definition of k is a part of S again, so P of k must be false. So we get another contradiction. So in any way we look at it, no matter what we do, we will always end up with a logical contradiction. Meaning that means that our initial statement that there exists a certain n, that P of n is false, must be wrong. Meaning that we can say that we are done. Because, like I said in the beginning, if this is not true, That means that for all n natural numbers, P of n must be true. And we're done. And just as another exercise, try to prove the same thing, but instead of regular induction, something that's called strong induction. Or instead of for all n natural numbers, instead of just assuming P of n is true, and then you show that P of n plus 1 is true, you instead assume that P of all the numbers from 1 to n are true, and you show that P of n plus 1 is true. And as a hint, it is a almost identical proof to this. And strong induction is more useful also because we're not just assuming the previous case. We're assuming all previous cases up until 1, which is useful. So again, try it on your own. It's pretty much the same thing, but just so you understand this proof. And you can also see how this proof pretty much works with our intuition. So our intuition says, well, if one must fall over, the second one must too, and then the third and the fourth, and so on. And that's basically saying, well, the first one cannot be false, because we're given that it's true, that like the first brick fell over. And it can't be anything other than 1, because that will mean that there was someone behind it that made it fall over, which would lead to another impossibility or contradiction. Meaning that all of them must have fallen over. And finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting problems and proofs like this in the future. And finally, that's it.